Okay, so now that we saw the building blocks, let's look at some of the motivations behind convolutional neural networks. Why do we use them? Why are they so useful? And why do they work so well? So what's really useful from CNNs is that they can learn useful features from images automatically. So we don't have to do any kind of we don't have to tell the network what to learn. The network learns for itself. Classically, this was done by hand. So you would have some people whose job it was to figure out some features that your classifier should look at and handcraft these features. So you can imagine how painstaking this is. But it doesn't mean that it doesn't work well, though. So for example, a really popular filter for edge detection is what's called the Sobel filter. So the Sobel filter was designed to extract edges from images. So here we have an input image. So it's a series of black followed by white. So, and here we have a kernel that is a Sobel filter. And this Sobel filter, what it does, its goal is really to extract the edges of our image. So if you applied this convolution to this specific image, the resulting image that you would get is what's shown here on the right. And this is really the edge that's been extracted. So here we have one edge of this image right in the center here, and we extract this edge. And for a very long time, edge detection has been used, and edge detection is still widely used, and it's a very useful kind of feature. But again, we have to work very carefully to handcraft these features. So let's look at an example. Say we have some kind of image, and we use our Sobel filters on this image. We can use horizontal and vertical Sobel filters, and the output that we get is this edge map of our feature. So again, based on this, we can then try to extract more and more features to try to understand what's in our image. But it can be very hard and very time-consuming to come up with these features. And you can imagine if this is your job, you might do a very great job on one specific data set, and the day that the boss comes in and says, from now on, we need to classify some different kind of images, all of a sudden you have to start that hard work from scratch. So when we apply convolutions to images, we can extract some high-level features, but again, it can be very challenging and limiting, especially in terms of resources. So what's really interesting is that by using the convolutional neural networks, not only can we extract features from a high level directly from the image, but we can also extract features at later layers in our image. So we're extracting features from features. And now you can imagine if you're trying to extract features from features, it might be really, really hard for someone to come up with some good filters for that. Now the network is able to learn these automatically. So here's a good example. So these are some of the filters learned by AlexNet, which is an architecture we're going to look at. So AlexNet was trained on a bunch of images of cats, dogs, and all sorts of different categories. And it turns out that it was a really good architecture to classify these objects. And these are the kinds of filters that were learned. So we saw that the Sobel filter was able to detect some edges, but here we see all kinds of different features that we can learn. And they're very complicated, right? If you start looking at them, you see that you see some edges being extracted, but also some different kind of gradients. And also, it plays around with the colors of the images. So if a human had to come up with this, it would be really hard. But in this case, we set it up as an optimization problem, and the network sort of converges towards this best solution. Another motivation for CNNs, so in MLPs, the way that the problem is set up is that every input contributes equally to the output. So here we have a little bit of a sketch of this. Here we have our output feature map, and we see that this input contributes equally to every single one of these outputs. In the case of convolutional neural networks, we're forcing the network to focus on local patches. So these outputs are only, this input here only contributes to its neighboring outputs, not to the whole bunch of it. And it turns out that this is very useful, and that the networks can actually generalize much better than with MLPs. We also have this idea of a receptive field. So we saw that so you might think that it's maybe a disadvantage when using the convolutional neural network because we're not getting the whole picture from the previous image. But it turns out that we have this concept of a receptive field in convolutional neural networks where the previous input might only contribute to some layers, but then they have information from more and more. So as you propagate further and further into your network, you actually end up getting many, many more contributions from the entire image. So you're first focusing locally, but as you continue going deeper and deeper into layers, you're actually getting representations from all over the place from your image, and you're combining them in nonlinear ways. That's a lot more powerful than the multi-layer perceptron. And again, we can think of this here also for our 2D system. So here we have our kernel, and we'll get this specific output. So the output right here on this cell will be the combination of these 3 cells. Now, as we continue, what we'll get, say for example, if we only go over this 5x5 patch, we'll end up with a 3x3 patch. But this 3x3 patch is made up from the information of this 5x5 patch, right? So already in a 3x3 patch, we have the information from a 5x5 patch. And if we do one layer deeper, this next 3x3 patch will have the information of the previous 5x5 patch, which actually has the information from the previous 7x7 patch. So as you go deeper and deeper into your network, this receptive field is actually giving you better and better representations to your network. We also have this concept of parameter sharing. So the same weights are used as different areas in the image. And again, if we think about this in the context of looking for ears or images in an image, this is very useful. In the case of an MLP, you would have to learn to look for ears and images at every point in your image. Now we're using the same features at different areas. So we have our sliding window. If it's detecting an ear or a mouth at one point in the image, it's looking for that same ear or mouth everywhere and can then combine that information. So we have this idea of parameter sharing, and it also happens that this requires significantly less memory, because again, we have these parameters that we're sharing across the entire image. We don't have to learn parameters for each point in our image. And this idea that, again, these kernels can extract similar features at multiple places in an image. So if it figures out that looking for a mouth is important, it'll figure it out for the whole image. It doesn't have to figure it out at multiple places in the image. Another interesting point is that convolutions are equivariant to translation. So what does that mean? It just means that if you translate your input in space, your convolution will also be translated. So that's a very useful property. If you classified a dog and just shifted it over, you still want to expect to classify that same dog in the image. It's not because the dog was shifted over just by a few pixels that all of a sudden you should be expecting to classify something completely different. And repeating this point again is useful features that have been learned can be reused at multiple stages in the image. So again, think of this mental image of if you were able to detect lips or ears or eyes, then you can detect them at multiple points in your image. So now let's take the time to consider a real example of a CNN. And this one has been around for a very, very long time. So it's called Lynette. You're going to play with it also in the tutorials today. So it's called Lynette because it was designed by Yann Lequin. Yann Lequin, who is very famous in the deep learning world. He's the chief AI scientist at Facebook, former colleague of Professor Bengio as well. They've received the Turing Prize together along with Geoffrey Hinton. So this was in the 1990s, right? So no one was really working too much on CNNs and convolutional neural networks in the 90s, but Yann Lequin and Yoshua Bengio were working on these, and they were trying to classify handwritten digits from the MNIST data set. So this MNIST data set, you saw a bit of it earlier, you saw a bit of the MNIST data set yesterday. We're going to look a bit more in depth at the MNIST data set today, but really what it consists of is a set of handwritten digits. So you have approximately 60,000 handwritten digits and their associated label. So this would be represented as a 0, this would be represented as the 1, and the task is given an input image. So if you're given a 2, you want your network to recognize that there is a 2 in there. So again, here's our problem statement. So say we have our 8 here. You want to be able to figure out somehow with a high degree of confidence that you're looking at an 8 in this image. And hopefully, if you've trained your network accordingly, the output that you get represents an 8. So here's the version, well, here's the architecture of Lynette. And again, try to think of these building blocks that we were talking about earlier. So we have our input image, which is a 28 by 28. And in this case, this is a grayscale image. So there's a single channel in our input. We first start with a layer of convolutions. So again, here we have the different parameters that we were talking about. So the kernel size is set to 5, the stride is set to 1, and the padding is set to 2. This is followed by a max pooling operation. So again, we're reducing the size of our feature map. And then we go ahead and apply another convolutional layer. Followed that with another max pooling layer and some fully connected layers. These fully connected layers will then allow us to go and calculate a softmax. We then can get a probability distribution based on our image, and we can compute the cross entropy and backpropagate the entire result. We do this over the entire sets of images, and then we can get a pretty good optical character recognition device. So in this case, we're able to classify very well digits from 0 to 9. And this is what you're going to be building in the tutorial today. So yeah, again, just notice that this network is comprised really of, it's essentially convolutions, pooling, and fully connected layers. And this was a model developed in the late 90s, and this is still true of most architectures today, that is just convolutions, pooling, and fully connected layers. And later on in the day, I'm going to introduce to you some more modern architectures, and you'll see how this is still true. So now let's look at I really like this demo, so hopefully the internet connection is happy with us today. Maybe it won't be. Oh, okay. So someone has implemented Linnet, so this architecture that we were just looking at, such that you can visualize it in your browser. So what happens here is we draw a number. So let's draw a random number. So let's say maybe the number 3. Oh, that was actually harder with this trackpad than I thought. Let's start that over. Oh, this is hard. This is not my trackpad, by the way. All right, well, the network is definitely confused, all right? And I don't blame it. This is not really a good-looking number. But what you can see, the idea here is what happens in the classification stage. So we have our input, and we have our different layers. So you can see here our different convolutional layers and our different outputs. And then we have our pooling stage here. So you can see how this is reduced in dimensions. And it's actually really neat. You can see the different filters that are being used. You can see at what point in the image it's focusing on. You can even zoom in and out of it. And again, you can continue going into your network all the way to your fully connected layers and your prediction, which in this case is a 1. Let's try to get one that actually works. Maybe I'll try an easier number. I guess the 7. Maybe not the best implementation of MNIST, but you get the idea. So the link is in the slides. You can try this on your own. Try to see if you can draw numbers better than I can. Hopefully, this network can detect these digits better than it detects mine. But again, a really, really cool tool to visualize what's happening with MNIST, because sometimes it's a little bit tricky to understand the connection between all the different convolutions and the operations that are going on.